And the second announcement is that when you ask a question, if you can please give your name first so that we can follow up on that later on. So let's go straight to the chase, and let's have a very nice lecture from Mark about the radiative.
Thank you. Well, good morning. It's so nice to be back here at the beautiful school. I was here about a dozen years ago, and the topic of the week was everything you need to know about exoplanets. And I think I talked about how you do atmospheric modeling of exoplanets, and I probably spent a few minutes on clouds, and so it's so funny, emblematic of the progress in the field that now we can have an entire week just on something that was maybe 5 minutes of the school a dozen years ago. So what I want to tell you about today, after we dived in yesterday with Christian, talking about all of the physics that we really should be thinking about when we consider the role of clouds. And so this morning, I'm going to zoom out a little bit and talk a little bit more about the big picture problem, and with brown dwarfs, which we've studied so well, and exoplanets, and then give kind of an overview of some of the other modeling approaches. Christian gave the full physics, think about everything approach, and I also want to cover what other ways of thinking about the clouds are. And then I'm going to move into something that's key is calculating the actual opacity, and what are some of the issues in calculating the cloud opacity. Depending on how the time goes, at the end cover some of the outstanding issues that have not yet been solved, and set up the activity we'll be doing in the second portion of the morning. So I always this is one of my favorite solar system images. This is a false color image of Saturn collected by Cassini. And the red is the 5 micron channel, which is a region of low molecular opacity in the giant planets. And so you can see deep flux emerging from inside the planet. And you can see that it's sculpted by the cloud decks in the atmosphere. And then the blue and the green channels are from visible flux, light scattered off the rings and the atmosphere. And so if you imagine Saturn as an exoplanet, and you get a spectrum, what is it about the planet that controls the spectrum that you get? And obviously there's the mass, the composition of Saturn. You'd like to learn that. There's all the issues of the interaction with sunlight, how the incident light heats up the atmosphere, scatters off the clouds, and the aerosols and the gases. There's, of course, the thermal emission. The photochemistry, we're seeing a little scattering from high altitude hazes there in the northern hemisphere, produced by photochemical reactions of methane with incident UV light, producing particles that are important to take into account. And of course, the clouds and the atmospheric dynamics, disequilibrium chemistry, it goes on and on. So all of these things ultimately impact the spectrum that we get, and we're trying to learn about all of these things from the spectra. But as you can see by just looking at the image, a key thing in attempting to extract all this information is what are the clouds doing. And so you have to have some approach to characterize the clouds to try to get at everything else that you'd like to know about. So let's say a little bit about what we know about brown dwarfs and young giant planets. I went to, I think, the second meeting that was ever held on brown dwarfs and exoplanets. It wasn't the famous discovery meeting, but it was one a year later in Tenerife. And early on, because they were studied at the same time, there's about the same number of objects, all the meetings were held together. And then ultimately, brown dwarfs and exoplanets kind of diverged. But we learned so much from looking at the problem of clouds and brown dwarfs. And so this is just to remind you that brown dwarfs are objects that cool off over time. They're not hot enough to sustain nuclear fusion. And so here in this figure, the blue lines are objects which are massive enough to sustain fusion, become M dwarfs. And then the green and red lines are less massive objects that cool off over time. And so at any given effective temperature, say 1500 degrees, say a 5 Jupiter mass object might reach that temperature after 10 million years, and 50 Jupiter mass out there in the green would reach that temperature after 5 billion years, or 4 billion years as they cool off over time. So by studying what's going on with the massive brown dwarfs, it gives us a window into lower mass objects like young Jupiters. The temperature, so we have a whole, because brown dwarfs are their own free-floating objects, we have great spectra. For example, here's an M dwarf. As we go to brown dwarfs, the molecular lines get bigger. We start to see substantial water features. Even cooler to like a T dwarf, we start to see methane. The molecular features are even deeper. And finally, we're down here to Jupiter, where the near-infrared spectra is reflected light, but we have thermal emission past about 4 microns or so. And we now have, for the directly imaged young Jupiters, an equivalent spectral sequence. This just came in my email this morning, but it's these are GPI spectra of young planets. But you can see the same kind of sequence from the relatively muted high temperature spectra down to the lower temperature objects, 51 Area B, about 700 Kelvin, with the nice deep molecular features. And so here's a sequence of models. This is a nice slide from Caroline Morley. The dashed lines show condensation frontiers for various species. And so where the temperature profile crosses the condensation curves, we expect from the equilibrium chemistry. And Christian told us we can't just trust the equilibrium chemistry yesterday, but it gives us a map to what to think about. So where the temperature profile passes one of these condensation curves is where we would get a cloud base. And so if we look at this, say, 1600 degree profile here in the middle, we can think of it as from Katrina Lauder's, this sequence of clouds with the high temperature perovskite, corundum clouds down at the bottom. We move up to the iron and silica clouds, and then higher up still the alkali clouds. This profile doesn't get cold enough to cross the water or ammonia curves, but if it's something cooler, we would have those clouds up at the top. What do the clouds do? Let's imagine a thermal emission spectra, and we're looking down into the planet, and maybe we have a region of relatively low opacities. This might be, say, J band. The peak of J band, there's less molecular opacity, so we can see deep, and we see flux emerging from deep in the atmosphere. And since the temperature increases with depth, we see a lot of flux. So it's bright. If you can think of this as brightness, temperature, or flux, it's brighter at the peak of the band. As we go off into the wings, there's more opacity. We can't see as deeply, and we're not as bright. Now, if we slide in a cloud into our atmosphere, we no longer, if the cloud's optically thick, we can no longer see the flux emerging from deep in the atmosphere. So that's going to shave off the peak of the band. But if it's the same effective temperature, the same total flux, we have to conserve flux. So the upper portion of the atmosphere has to transport that heat. The atmosphere heats up, so it's less cool, and the wings of the bands come up. So clouds tend to make our spectra a little bit grayer. And here's an example of showing models. Blue is a cloudless model, and brown is a cloudy model. And you can see that it's here in J band, it's shaved off the peak quite a bit, and it's brightened up, for example, K band. So in general, you can think of clouds as making the near-infrared, in particular, a little bit redder. This is the famous color magnitude diagram for brown dwarfs. This is absolute J magnitude on the vertical axis, J minus K color on the horizontal axis. And there's M stars up at the top, and then the population of field brown dwarfs. This is a brand new figure from Will Best, who just completed his PhD a week or two ago, with adding getting new parallaxes and cleaning up the objects in this figure. But you can see that what's happening is along the right, those are the L dwarfs, and as they cool off, they get fainter in J, they get redder in J minus K. And then there's this transition to the blue, where it turns out methane starts to show up in the near-infrared, and the clouds go away. I'll say more about that in a second. The brown dwarfs come across, and then they continue to cool off. So if we put up a sequence of cloudless models, this is our brand new cloudless models from my group, or the colored dots, And you can see that for the M dwarfs, you don't need clouds. For the mid T dwarfs over here on the left, you don't need clouds. But every other departure on this figure you cannot understand without including clouds. So clouds are fundamental to understanding almost all the objects among the brown dwarfs. You have to have some kind of approach to the clouds. And here's our older model set, just where we've tried to do that. This is K versus J minus K now. And our previous models were somewhat successful, but not very. And the problem is, since this is 2008, since that time, well, let me, before I get to that point, let me just show you some, for the colors now, let's look at some spectra, again, to try to give you a handle on what do we know about the clouds. Here's the color magnitude diagram, again, on the right with the big dots showing you where the object I'm showing you is. This is an early L dwarf and L1. The red is one of our cloudy models. We're going from 1 micron out to 10 microns. The objects I'm showing you have IRS spectra from Spitzer. So, okay, yeah, so J is, yeah, so here's what, this 1, 2. So here's J band, and here's, yeah, K, so this is JHK. And then we've got L band and then the IRS spectrum. But if you compare that to a cloudless model, it looks nothing like it. Oh, great, thank you. Here's a cloudless spectrum in blue. So even for this early L dwarf, you really need clouds. Here's something more of a middle M dwarf down here in the middle. Cloudless is in blue, cloudy is in red. It's not a perfect model, but you can see the clouds are really required to fit this. Let's go down to an L8, right down here at the bottom right of this sequence. Data is in black. Again, the model is now getting less good because the clouds are very important. But you can see, crudely speaking, the red is right, whereas the blue, a cloudless model, is nothing like the data. You've got to have clouds. But notice our best fit here is 1400 degrees. Let's go now to a T-dwarf. We've popped across on the color magnitude diagram. Cloudless model, no clouds at all, fits remarkably well. But look at the temperature. It's 1300 degrees. So in 100 Kelvin, we went from clouds are massively important to there's no clouds at all. This is the principal unsolved problem. And there's been some new ideas I don't have time to go into, but this is still the principal unsolved problem in brown dwarfs, is what happened to the clouds. And here the red is a cloudy spectrum, which looks nothing like what we have for this object. Secondly, kind of the other big issue in brown dwarfs and young giant planets is here's the same sequence I showed you before, and over the last decade, there's been the discovery of all these young brown dwarfs. The directly aged giant planets like HR 8799 are down here at the bottom right. So there seems to be their own low gravity sequence that's offset from the standard field brown dwarf sequence. And so they're redder. Clouds seem to be more important, maybe because it's lower gravity, they're lofted higher, and they hang around to lower temperatures before the clouds go away. And so this whole low gravity sequence down to the directly imaged planets is also not well understood yet. So that's a long wind up, but clouds are important in brown dwarfs. We know a lot about brown dwarfs, and it gives us some context to thinking about the exoplanets. Hot Jupiters, I'm not going to say much about. Vivian's going to give a whole lecture on this tomorrow. But here's kind of the principal difference is that with the hot Jupiters, we're irradiated from the top, whereas brown dwarfs, all the flux is coming up from the bottom. And so we get a very different temperature profile. And so we're kind of crossing the condensation curves less steeply. Maybe the clouds are behaving differently. The atmospheric dynamics is much more important. So they're their own separate class of problems. And here's just the famous Singh figure with all of the transit spectra and the varying strength of the alkali absorbers and various slopes into the blue of these hazes or high altitude clouds. A lot to think about. What about thinking a little bit about the future for the directly imaged planets? with WFIRST, we'll be looking at reflected light in the next decade. Maybe the 30-meter telescope should be able to do some planets in reflected light. And further along, LUVOIR and HabEx, looking for the pale blue dot, are going to have to contend with cloudy atmospheres. And they'll also do a lot of great science with cool, larger planets. So when you now, instead of looking at thermal emission, thinking about reflected light, if we don't have any clouds, we have a relatively clear atmosphere. The blue light rarely scatters, say fairly high in our atmosphere. Redder light scatters less, so it can drill down deeper, where it can run into molecules at depth, like where the atmosphere is denser, water, pressure-induced capacity of hydrogen, sodium, potassium, methane. And so we don't get much reflected light in a clear atmosphere in the red. If we put a cloud in, though, both the red and blue light can scatter high in the atmosphere. And so when we do our exercise in the next section, you'll see this for yourself. These are geometric albedo spectra, so it's reflected light spectra, basically with the incident light divided out. Here's Uranus on the top, Jupiter on the bottom, and Pat Irwin would throw tomatoes at me if he had brought them with him this morning, but kind of to 0th order, we can understand the difference between, say, Uranus and Jupiter is that the clouds, the bright ammonia clouds, are more important at Jupiter. You can see the continuum flux is higher, whereas at Uranus, there's more methane in the atmosphere, other stuff's going on, but it looks more like a cloudless atmosphere because the cloud is relatively less important than it is at Jupiter. I'll be talking more about, because this is what we're going to be doing in the second session, but the geometric albedo was invented in the solar system by thinking astronomers looking at planets at opposition. So the sun's behind you, here's the Earth, the planet's out there, you're looking at the full disk, and for reasons to complicate our lives today, they divided the flux by the spectrum they measure by the incident flux and measure it relative to a Lambertian disk. So a disk that scatters equally into all angles. Really, I think exoplanets, I've been talking to people about this, we need to divide our own albedo measure because it doesn't make any sense. And in fact, the difference between geometric albedo and bond albedo, TPFC, which was this multi-billion-dollar mission studied by JPL in the early 2000s, they used the wrong albedo early on to measure how bright the planets were going to be. So it's just a mess. So we need an exoplanet albedo, but that's a different topic. But anyway, so clouds matter. So here's a example of clouds matter. And I've showed this figure for years. I kind of like it. Imagine the sun's over towards me. Here's Jupiter. We take Jupiter, we move it in closer to the sun. The ammonia clouds evaporate, so then we would see bright water clouds underneath the ammonia clouds. Maybe Jupiter have much different spectra, and we move Jupiter closer in, the water clouds evaporate, and we'd have this nice, beautiful blue Rayleigh scattering Jupiter with the red photons getting absorbed. Except now the water's in the atmosphere, the H2S is in the atmosphere, ammonia is in the atmosphere, you're at 1 AU, so you're getting irradiated, and it's going to be worse than 1972 Los Angeles smog. And who knows what it's going to look like from the photochemistry. So there's a whole nother layer of complexity that we ultimately have to think about. Finally, so I've told 4 things, examples: brown dwarfs, transiting planets, I sort of skipped over, which we know it's important, reflected light planets, and just to do forward models, figure out the energy balance of these things. We've got to understand the clouds. Here's a cartoon I got off the web. There's thermal flux coming off the bottom, incident flux bouncing around. If there's something that doesn't condense, some gas that doesn't condense, say has a constant abundance, if I'm plotting abundance over here in a cartoon sense, here's a constant abundance, but if I'm trying to measure the abundance of this gas, say this is water or this is methane, what the column of methane I see depends on where the cloud is. So if this is my, I think I found a habitable Earth, and I want to know I see methane in the atmosphere, I want to know how much methane it is, I've got to know where this cloud is so I know how much column of methane I'm seeing. The water is going to condense, the water falls off, and maybe I'm measuring the water abundance up here above the clouds, but yet the real water abundance is higher below the clouds. Or maybe it's a desert planet and there's no cloud at all, and this really is the water abundance. So it's really important to try to have some context for how to handle these clouds. This is just one of our modeling papers. Lots of people have modeled these atmospheres, but you can put in all the equations. And this is from my modeling review with Ty Robinson. But a key point of trying to derive a temperature profile for a given planet is how are we scattering the light? What's going on with the thermal flux? And scattering is crucial to all of these problems, the particle scattering. And so again, you've got to have clouds. Of course, this is an old problem for planetary science. Of course, for the Earth, is how do you handle the clouds? Our own group uses this paper from Toon et al. Of rapid calculations of radiative heating rates in inhomogeneous, meaning the atmosphere has discrete decks of clouds, multiple scattering atmospheres. And so there's and I'm not going to have time to really talk about all this, but there's a lot of literature in how you choose to go about trying to model the actual radiative transfer in these atmospheres. And you have to make wise choices, and there's always trade-offs between speed and accuracy and what you're trying to accomplish. And so for all of these reasons, we've got to have some context for the clouds. And so what do we want? What do we need to know? Cloud composition, particle sizes, the vertical and horizontal distribution. This is a figure of a dust storm, I think, in Africa, and you can see the clouds on top. So we've got one class of particles scattering light down here and a different class up here. They're separated horizontally and vertically. And what do we need to know? We need to know the particle sizes, where these clouds are, what the optical depth is, what the single scattering albedo is. How do we get that? And to start with, we've got to have a cloud model. Christian did a great job yesterday pointing out that the first thing you have to decide on is what the atmosphere is made of. Do we start with solar composition? What's the chemistry doing? And I won't go into that again, just to remind you that, yeah, it's super important. And for example, solar composition, these are species that show up. In our own case, in our group, we look at equilibrium chemistry, see what species are going to condense. If the vapor pressure of a gas, if the partial pressure of a gas in the atmosphere exceeds the vapor pressure, then the particle is going to condense. Again, as Christian said, it's not that simple. There's going to be supersaturation. It's a more complex story. But to zeroth order, we can think of it that way, that as soon as the vapor pressure is less than the partial pressure, that's when we start to get condensation. And if you do that, some species like iron condenses out and makes little iron drops or iron solids. And it's a lot like water condensing, say, in the Earth's atmosphere. But in other clouds, like the silicate clouds, it's really more complicated. There's some chemical reaction between, in this case, 3 different species in which for you to make forsterite. And certainly, seed particles and things, this is unlikely to happen right from the gas, so it probably really does happen on seed particles, and it's a more complicated story. Plus, this is a micrograph of people trying to model dust formation in the solar nebula. And we imagine, in the rest of this talk, we're imagining the dust particles we're making as perfect little spherical Mie scatterers. But here in the lab, when you do it, it doesn't look anything like that. You get these little fingers, and they're not even, spherical. A lot of times you get little cubes. And so the point of this is it really is complicated, and we're going to proceed, our group proceeds from a very simple-minded point of view. So given all of this, how do you go about trying to say what's going on? And there's different sort of cloud modeling schools. Christian, I like to kind of describe her approach as sort of a top-down, where she thinks that there's seeds. You think of seeds kind of falling down from the top of the atmosphere, and then you get bigger particles. That's sort of how karma works, by introducing seeds into the atmosphere. There's also, you can just throw up your hands and say, I don't know how to do this. I still don't know how to do this. But you can say, well, we're just going to put in a slab. I'm going to put a cloud in at the cloud base. It's going to be 1 scale height high, and they're going to be 50 micron clouds. And you can, like Suji, who was a pioneer. Suji-san is a pioneer in brown dwarf science going back from his thesis in the 60s. He predicted a lot of these things would be important. And he looked at just very simple clouds like that and found good success. Adam Burrows' group has taken that approach. Really, if you think about the transit clouds where people add a cloud deck, a thick cloud deck is really it's a fixed cloud. It's a fixed gray cloud. And as you know, you can do a lot with that. There's chemical equilibria clouds, like the dusty clouds. The Ackermann and Marley clouds, I think of it more as a bottom-up, and that we're mixing the condensing vapor up into the atmosphere and trying to account for sedimentation downwards. So there's just different approaches. And what you choose is really driven by your needs, what's the quality of your data, how fast are you trying to get this to run. There's a lot of considerations. When I was looking at my old slides, I used to show this slides. I haven't shown it in a long time. But since from the solar system, there was this approach called the Rossau approach to thinking about clouds. And it was basically you calculate a lot of time scales, coagulation time scales, evaporation time scales. Here's log time in seconds. This is for Jupiter clouds. And then you sort of plot them all up and sort of stare at it and see, well, when does the coagulation time become longer than the fall time or the evaporation time? And it gives you some insight into what's going on. But Andy, who developed our cloud model, always said, well, I look at these and I don't know what to make of it. How do you know which time scale to pick or what's most important? But it does give you insight, and it's something to think about if you're trying to learn about clouds or think about clouds in a new context, is to approach it from the time scale point of view. So around 2000, when it was clear that clouds were important, I knew if we're going to be modeling brown dwarf clouds, needed to have a cloud model. And Andy Ackermann was down the hall from me, and he studied clouds in Earth's atmosphere. And I'm like, Andy, we need an exoplanet cloud model or a brown dwarf cloud model. And it just needs to be one-dimensional. And he looks at me like I'm nuts because, clouds are inherently not one-dimensional. You have updrafts bringing the vapor up. You have the solids forming. And he's like, well, and so I imagine like Titan. Here's my mental picture is we need this one-dimensional spherical planet with uniform clouds every place. And he's like, well, I can't do that. There's no such thing as a one-dimensional cloud because, this is why. So I kind of kept after him, and so he got interested in the problem, and he invented and so this is like he has to show this figure. This is how he got from some review article about how clouds and raindrops. I think this is like how raindrops form in Earth's atmosphere, right? And so, whereas we need a one-parameter cloud, right? We're just dumb astronomers, right? So. Anyway, I bugged Andy enough. So this is called the Ackermann and Marley cloud model, but it's really the Andy Ackermann cloud model. And I was the customer that said, I kept pushing him. It's like, well, here's what it needs to do. So you can think of me as representing the community, and Andy is the real genius behind this. But ultimately, he came up with this sort of one-dimensional model where we're transporting upwards the vapor and the condensate, and then downwards we have a rainfall of particles. And what his kind of breakthrough was, we're not going to try to do the microphysics. Christian told you to do it right, you have to think of all the microphysical processes. What we're going to do is not think about all the microphysical processes, and instead imagine that we have a tunable parameter, which originally we called F rain, and then he decided that rain meant water rain, and so we now call it SED for sedimentation. But it's a tunable parameter, and so when this parameter is large, it basically means the downward flux term is important. So somehow the atmosphere is making big particles that fall out. So the microphysics magically makes the big particles, when F set is big, so the particles fall down and the clouds are thinner, it's a smaller number of particles, they have less optical depth. When fset is small, it's the other way around. The sedimentation is less efficient, so the particles must be smaller. So somehow the microphysics is magically, with no science, is just magically giving us small particles. And so that's what we've been using to do our cloud modeling. And here's like a size distribution. This is from I think this is off Pacific stratocumulus clouds, but it's kind of a general rule of thumb in the Earth. This is size distribution versus radius, so how common different sizes are. And typically you have these small sizes where the droplets have just condensed, and then you have these big sizes where they've grown into big particles. And they really have their own independent sizes. The big particles are important because if this is the precipitation flux, it's how much mass is falling through the atmosphere. So the big particles fall faster, there's more mass, and so from the flux point of view, the big particles are important. But whereas kind of from the optical depth point of view, pi r squared times the number of particles, the little particles are really important. So what we do, what Andy came up with, is this log normal. He said, well, we'll cover both of these sizes with a big fat size distribution that attempts to account for both the big particles and the small particles. But really, like in a next generation model, or the microphysical models, you need to account for these independently. But so here's kind of an example, silica clouds. If you did not have any sedimentation, here's log pressure, so up is up, mass density to the right. So if there was no sedimentation, you have this big, tall dust particles all the way to the top. This is like the dusty particle, the dusty models of Chabrier and collaborators. Once you have rainfall, though, it flattens the clouds and makes them more compact. Karma, just as another example, is a model that also tries to do all of the radiation to account for more of the microphysics. Andy also was one of the principal authors behind Karma. So there's a lot of, when you get down to the guts, there's a lot of similarity between the Eddie said, our Ackerman and Marley model, and Karma. Here's a figure showing, I forgot, I think it was Peter gave this to me, Peter Gao, of hot Jupiter model set up, where again with Karma, we're introducing TiO2 seeds on which silicates grow, and there's vertical mixing. And Karma attempts to do all these processes while accounting for the microphysics. And here's particle radius, pressure in the atmosphere, 4-month time steps. And so if you take a lot of time and run the model, you can see, you start to get these different cloud layers at different sizes and different masses at various points in the atmosphere. So, the Ackerman and Marley model would have run 100 times by now, whereas this one we're still, converging. This is a long time trying to see what does Karma want to converge to. So again, it's just a different. What are your needs? What choices do you want to make? So let me give you. This is my quick sort of comparison of some of the cloud models that are out there. Just sort of some of the pluses and minuses. Again, there's no right or wrong answer. It's just what are the pluses and minuses of some different approaches. Prescribed clouds, great. You don't have to make a lot of assumptions, just a few parameters. They were an early indication of how the LT transition works. They can give good insight into what's going on. And if the data quality isn't great, like the early transit data, a slab cloud is just fine. There's no reason to go further. Drawbacks, though, you don't really know if you just specify something, how unique is that solution. Each fit is basically a one-off, and it doesn't really give you much insight to predicting how other objects might behave. And there's often, with these kind of prescribed clouds, there's no follow-up. Like, 50 micron particles fit, but why do you have 50 micron particles? The Con and Dusty, these are the old models circa 2000. These were reasonable limiting cases. They did not include any sedimentation. People still use them. You really shouldn't use them because we know that clouds form cloud decks, and the Dusty models just are not appropriate. But I've just put that up there. Christians. stuff. There is no question that she has done the most thorough job and it's the most complex models. Here's like the reaction list I stole from one of her papers. It's a steady state dynamical evolution. It teaches us that condensation is complicated. Probably we have dirty grains. If you were to go pick up one of these grains from a brown dwarf atmosphere and slice it in half, it's not going to be this little perfect, pure Forsterite particle. It's going to be multi-species dirty grain. And so I think this work is super important for helping us understand that. Maybe some of the drawbacks is, again, it's still so complicated. And I think sometimes, it may be hard to incorporate all these things into forward models and understand what's the relative importance of different ingredients for understanding it. Just blowing our own horn, I think, our model, it's well documented. We're finally going to put it up on GitHub. I've been giving it to anybody that asked, but we haven't, but Natasha's getting it up on GitHub for us. Developed by someone who does cloud models, terrestrial cloud models, Andy, and it works, reasonably well. The downsides of our model, it used to be not widely used by other groups. I think that's maybe not so much true. But there's no microphysics, okay? So you start turning the FZ knob and you really don't know why. You just hope that magically the particles appear that you say are going to need. We're using pure grain composition, and Christian has told us that is just not true. But that's what we do. And we've added epicycles to the model. We've added cloud holes and various things to try to improve the model. But the truth is those are epicycles. And so in summary, there's really there's no perfect treatment for clouds. I think the right balance of physics and simplicity has probably not been found. Maybe one of you in this room can take another crack at it. Don't feel like, oh, this has been, everything has been done. There's lots of room to try to do this better. If you're going to use something, be a skeptical shopper and think about, the pluses and minuses for what you're doing. So that's sort of end of part one of the talk, of kind of giving you the big picture overview and the models. I want to say a little bit about once we have a model, how do we go from the model to actual opacities that we can then include in radiative transfer. Yeah. So in the solar system, kind of the rule of thumb, maybe Pat can talk about this more later in the week, sort of in the upper atmosphere, in the solar system, giant planets, from observations of the photochemistry, which are good tracers of the atmospheric dynamics. In CGS units, they're sort of like typically 10 to the 5th, 6, 7, 8. It varies, the KZZ it varies with altitude in the solar system. We really don't know a priori and so we kind of start there in the solar system, it's those numbers. The GCMs on hot Jupiters point to lots of mixing, lots of atmospheric dynamics, and maybe KZZ could be 10 to the 10th in CGS units. You start to run into the sound speed if you get up, like I think it's 10 to the 12th, KZZ of 10 to the 12th. So you probably can't be higher than 10 to the 12th. It's not going to be 0, because we know when planetary atmospheres mixing, it's wave breaking, wind dynamics mixes the atmosphere. So it's only like 12 orders of magnitude in between. Yeah. So, but I mean, yes, and I think I skipped over that bullet on like the Ackerman and Marley is we haven't. I think a lot of the modeling we have done, and we've not varied KZZ all that much, and that's something that could be looked at more. Yeah.
Following up on that, if you're pushing towards super Earths and smaller planets, can you fit a similar KZZ value to terrestrial planets in the solar system?
I know less about that. Maybe Tony, do you have what's?
Actually, I was going to say, well, not something directly about that, but I think maybe one of the key issues with terrestrial planets is when you have moist convection, which behaves differently from dry convection turbulence. I think that's the big challenge as to how one goes about that. So, and maybe that there's a way to, if you have, I don't know, when you run these, are you running them in models that
Right. So we use mixing link theory in the troposphere to get KZZ. But then above that, strictly speaking, in a radius zone, KZZ would be 0. But it's not, right? We know there's like wave breaking and there's mixing and wind shear. And I think there's a rule of thumb in the solar system. It increases as like 1 over the square root of density. So we put that into our model. So, I mean, you've touched on something that gets swept under the rug sometimes, but it's really important, the KZZs. Especially like, so again, it'd be a skeptical shopper when you see a paper that said, oh, we fit the transit spectra of planet XYZ with FZ of 0.01. It's like, well, yeah, but what KZZ were you using? Okay, so let's say a little bit about everything you need to know about me scattering in 5 minutes. I posted 2 things, or gave it to Daniel to post on the website. Hansen and Travis is really the go-to review article to tell you about me scattering. And this is, global warming, Jim Hansen, 1974. It's still a very readable paper. You should take a look at it. Jim Pollock, who was my postdoc advisor, sort of took the figures from here, pasted them on blank pieces of paper, and wrote notes around it. So this is sort of the lecture version of this paper, but Jim he draws on the figures and makes comments, and it's still very digestible. So he used to teach all his new postdocs. He would teach them, me scattering, and these are the notes he used. So take a look at that. It's a little bit more in depth than what I can do here in a few minutes. So now we've got our wonderful cloud model. We know the sizes. We have all these perfectly spherical particles. We know what they're made of. How do we handle their interaction with radiation? And so you can imagine incident light comes and it hits our particle. Some of the light is absorbed inside the particle. Some of it scatters at some angle. The particle itself can emit light. And the way we approach this is to define cross-sections. The physical cross-section, or the geometric cross-section of the particle is just pi r squared. And just like with molecules, with molecular opacity, you can think of it as like these centimeters squared per molecule as a physical cross-section. And so likewise, we can scale the geometric cross-section by these Q parameters that tell you what the cross-section would be for absorption, scattering, or extinction, which is the sum of the scattering and absorption. And the emission cross-section is the same as the absorption cross-section. The single scattering albedo is just a measure for a given particle of what's the scattering cross-section to scattering plus absorption. So if there's no absorption, this is 1. If there's absorption, lots of absorption, and not much scattering, the single scattering albedo is small. And then there's also the phase angle, which is what direction does it's like a probability of what direction, how likely the photon is to scatter into any given direction. And the integral of the phase function over all angles is 1. And for an isotropic phase function, where light's scattered equally in all directions, the phase function would be 1. Rayleigh scattering is more of this double-peaked forward and backward. Typical particle me scattering tends to be more in the forward direction. And you can have various phase functions to try and analytic phase functions that try to describe the results you would get from me scattering. So how do we compute this? There's something called geometric optics, and in Hansen and Travis, the review article, they talk about this. You can kind of conceptually think, here's a photon coming in. It can scatter. It can go into the particle, bounce around, and come back out. And you can sort of try to keep track of these things from just geometric optics and gain some insight. But what today most people use is Mie theory, which is an exact solution of Maxwell's equations. And you can go download a Python module that does Mie scattering and think that you're in business. But again, it's for perfectly spherical, homogeneous particles. And when you do that, you can get all kinds of results from a Mie scattering calculation. So here's, for example, phase function versus scattering angle. And let's just look at one case. This is for a given value of x is 2 pi times the radius divided by the wavelength. So you pick a wavelength and a radius. And in different cases, where here for a given value of the real index of refraction, here's what the phase function looks like after you run your Mie scattering calculation. So at zero scattering angle, so going straight ahead, you tend to get this forward scattering peak. Then try this broad peak, you go around, and then like you can see it better in some of these other cases. You get these rainbows scattering around 120, 130 degrees. Rainbows, and then you get a backscattering peak that's called the glory. If you've ever flown in a plane looking down at clouds below you, you can see the shadow of the plane and then a bright circle around it. And that's this backscattering peak you see here. The diffraction peak up here in front gets narrower and higher as the particle size increases. If you can measure this is a way to estimate sizes. A classic example is you're driving, you don't wash your car for 2 weeks and you're driving towards the sunset and then your windshield lights up because the light's all getting forward scattered by the particles in the windshield, and that's this. I think that's all I want to say about this. But the detail, the shapes, what's changing here is the ratio, these different cases, is the ratio of the particle size to the wavelength. And then, like the left and right panel, is different indices of refraction. This is the scattering efficiency, this Q scat, as a function of the size parameter, 2 pi a over lambda. And for what's being shown on this figure, this isn't from the Hansen and Travis review, is the scattering efficiency with if you have a single particle size. And all of these wiggles from the high, the low frequency wiggles, this big peak, you could say the scattering at when 2 pi a over lambda is around 6 or 7, so 2 pi is 6. So when the size of the particle is comparable to the radius, to the wavelength, you get this big, highly efficient scattering peak. But this is really an interference effect. This is a fringing effect in the particles. And it comes from having a very narrow size distribution. These B's here, let me just skip ahead. These are particle size distributions. And when B is small, they're very narrow. This is called a Hansen distribution. When B is larger, it gets broader. And you can see that when you use with a size distribution, it washes out these interference effects. And so in the real world, you never want to just, to go download a Mie code and say I have exactly one size of particles, because you get all these interference effects. Whereas in nature, you always have a range of particle sizes, and it washes that out, and you get something that looks more smoother. If you look at Eddie said, Ackerman's code, he does a really nice job of taking different bins and integrating over a size distribution. And that's a nice example of how you actually do this in practice. The other thing to point out is you can get particle sizes, but you need a large wavelength range. So for example, here, if we think of a single given particle size, if we can measure this Mie scattering profile, we can get it the particle size by comparing to the calculation, but we need a large wavelength range. Say from a micron to 10 microns would be nice. So if you're going to go buy a multi-billion-dollar space telescope to look for habitable planets, you want one with the largest possible wavelength range. So for example, LUVOIR as opposed to HabEx. So it's a serious comment, though, that if you really want to characterize clouds, you need more particle sizes. You need more wavelength range. And here's just some other particle sizes you could use. Finally, here's single scattering albedo as a function of the imaginary index of refraction, which depends on the composition of the grain. And if there's the imaginary index is small, the albedo is high. Kind of counterintuitively, if the imaginary index is very large, the photons don't even want to go in. And so you also get a high single scattered albedo. But these intermediate cases, you get a lot of absorption. And likewise, here's the phase function. You can read about this in the review article. And so finally, here's just an example. Here's big particles, opacity from 1 to 100 microns. Big particles would look like this, small particles, very different. So we need indices of refraction. Where do you go get those? There's online repositories for this. Daniel Kitzman here in the room has done a nice job of going through and collecting a lot of indices of refraction and making them available online. But again, buyer beware. You have to really look and say, well, why did he pick these values? If it's something really important to your research, you really need to critically evaluate. I can't stress this enough because people measure these in lab. In the lab, it can be hard to measure. Sometimes people interpolate over between different measurements. And so you really have to look at it. And also here, this is for forsterite, key brown dwarf absorber or condensate. Over here on the right, we have iron. There's a solid solution in nature between the pure end member of magnesium and the forsterite and the iron end member. And when you put a little bit of iron in, look at that, it really changes the imaginary index. So what should you use? And it makes here, right where we're looking, a few microns, it makes a big difference. So if you've got all that, let me just show you an example of how this matters. This is an IRS Spitzer spectrum, a brown dwarf, 6 to 14 microns. Here's a model. The model is fairly flat. Look at this, there's this big scallop missing. We noticed when we first got the IRS data. And so we said, well, we know there's a silicate feature. You can do me-scattering. This is Q absorption for silicate particles. Here's amorphous particles. Here's crystalline particles. What are you making in the atmosphere of a brown dwarf? It's probably amorphous, but who knows? So you can do the me-scattering. This is just from the me-scattering. These are different sizes, tiny particles, bigger particles. With really big particles, you don't get this feature. For smaller particles, you do. And so you can use that to try to constrain what's going on in the atmosphere. Ben Birmingham, he's on the right of the two, has written a retrieval code he calls Brewster, but it can do slab clouds, cloud decks. I won't go into all the details, but he can retrieve on different compositions. And he's applied this, for example, to brown dwarfs, to the L dwarfs. Here's 2mass 224. There's near-infrared data, IRS data. The models are in the colors. They don't fit very well. I won't go into that in detail. But then he runs the retrieval on it, gets temperature profiles. But the key thing is he finds you'd need a deep iron cloud deck and a shallow silicate cloud deck. And the silicate cloud deck has to be small particles. And so here he shows both the data and his fit. And you can't see the fit because it's right on top. Let me zoom in. Here's the near-infrared. Now you can see it. Nicely job there. And here's the IRS data. And it comes down here and gets that silicate feature. And the reason it's able to do that is by using small particles, like 10 to the minus 2 microns to 1/10 of a micron. So pretty small, surprisingly small. Eddie said wants to put fat particles up there, like 5 micron particles with a fat size distribution, and which just washes out that feature. We don't see it. So there's an example where particle size matters, the composition matters, but if you put everything in correctly, you get a nice match to the data. Another real quick example is H2S. Kevin Zonley noticed that H2S photochemistry could be really important for the warmer Jupiters, like a 600 Kelvin Jupiter. H2S, there's mixing into the atmosphere. You end up with SH, and then you end up with sulfur, which then makes sulfur rings, S8, and the sulfur can condense into hazes. So you might have hazes of sulfur dust. Here's the real and blue imaginary index of sulfur, and look at this. In the blue, this huge, this the K gets big. And sulfur compounds have been suggested. There's a mysterious darkening in the clouds of Venus that might be due to sulfur compounds. That's an old idea. But if we plug into the Mie scattering and then calculate the albedo spectrum, which Peter Gao did, you see that here's a cloudless model and then a model with a sulfur haze. It brightens it up a lot in the red, and then you get this big, huge blue absorption. And so this is something like LUVOIR could see, or maybe you could see this in transit. So that's kind of to start to wrap things up. One last quick point is, again, we've talked about this before, there's different kinds of albedos. There's bond albedo, which is energy in versus energy out, and it's integrated over the incident flux. And so you can take the exact same planet that, say, is reflective in the blue and absorbs in the red. It can have a high bond albedo if you're around an early type star, which is blue, and then a much lower albedo, bond albedo, around a later type star because it absorbs more of the incident light. Whereas a geometric albedo, which is what we're going to do in the next session, is just a given spectrum. It's a reflectivity measurement. And I think I'll skip that. So real quick on ongoing problems when you try to include cloud models and calculate temperature pressure profiles. Sometimes it doesn't converge because you have a profile, you put a cloud in, the cloud traps the infrared radiation, the atmosphere heats up, and maybe it heats up enough that it no longer wants to have a cloud. And you can get these, especially as somebody that has an important absorber like water vapor, you can end up bouncing back and forth. Here's a movie Caroline Morley made. Here it is. So we're running our model trying to converge. There's water condensation. And look at that, it just doesn't want to be happy. It keeps, and this is really the problem with trying to do a one-dimensional cloud, right? Is there's just no good solution. And so what we've done to try to solve that is say, well, clouds are patchy, and we have a clear column and a cloudy column. In some terrestrial GCMs, this is done at the subgrid scale. That's probably not done as much anymore, but I think that was an older solution. But we've adopted that, and which is a figure from Caroline. So we have a clear column and a cloudy column, and then add up the flux. And the clear column kind of acts as a ballast and stabilizes the calculation and helps us calculate a converged profile. But it's really, are there better ways to do that? Variability is a big issue, and the variability may be telling us a lot of information if we can model it correctly about the cloud structure. And Daniel has taken a huge lead in getting great data sets for variability. This particular figure is just from Jackie Radigan showing time variability of the flux from a very variable brown dwarf. Look at this, 20% variations in flux. There was just a paper on the archive from Tan and Showman last week where they just do a single one-column calculation with clouds, and here so you can see the temperature profile is bouncing around, and all of this is just from the radiative feedback of the clouds and the flux. And the KZZ is changing, the mixing ratio is changing, and they produce plots of the flux out the top, which vary, and probably is telling us something about the brown dwarf variability. So let me conclude here. Sort of this brief overview is, cloud is super important. It's an unsolved problem. I've been saying this for a long time, as it needs to be better. We've got a whole school at this. So, people in this room, I hope you can do better than we have. There's been some successes, but, how can we leverage this to the whole domain? The interaction with radiation isn't trivial. We'll be give you more of that when we do the exercise. There's lots of pitfalls. And I can't stress enough how important it is to test your codes. There's analytic solutions you can compare to. You just have to be careful because there's lots of ways to make mistakes. All of the existing models represent various preconceived notions. And you should treat everything with a great deal of caution, but go out there and innovate. And because we're certainly going to need it with JWST, there's no question. The generation of LUVOIR or HabEx, we're going to need cloud models to interpret this data. So I'll leave it there. Thank you.
Thank you, Mark. That timing is perfect. We have time for a few questions. So please tell your name first. So.
Well, I mean, you notice so in that case, the silica clouds are much higher. So those up in the radiative region, and so maybe it's saying that the KZZ is smaller than, say, the Ackerman in that particular brown dwarf than we've been using. So we haven't done that, but we should then go run the cloud model and see what do you have to do to KZZ to make those small particles. And it's also probably telling us that we assume a log normal fat size distribution, which is wrong for those clouds.
Daniel Paul, when you were talking about the Mie scattering, you were, I think, I don't know if all the models do this, assume homogeneous particles, but yesterday, for example, we were talking about different kinds of stuff blending together into a single particle.
Yeah.
Do you think that would matter much?
Yeah. I don't mean to be glib, but yeah, there's Mie scattering codes that have a core, and I don't know now if there may be even you can have multiple layers, but you can do. I mean, if you're just solving Maxwell's equation inside the particle, and you put the boundary conditions in the interior, and you can solve for that. Also, fluffy particles can behave. You can get a big fluffy particle, and maybe the fluffy particle acts as this low density, maybe it's easier to loft higher in the atmosphere, but yet the individual components of that is what you really see in the scattering. So you can have this kind of weird combination of maybe it acts like a big particle for dynamics and small particle for the radiation. So there's a lot of complexity, and plus these, what Christian calls the dirty particles would certainly change that. Well, I think for where we are now, it's probably okay, but it certainly is not perfectly right. For example, I mean, there's a lot of literature looking at what if you have, for example, cubic particles. How does that compare? And there's actually transformations you can do from cubic particles to the equivalent Mie size, or from flat particles. So there's people have thought about those kinds of things, but really, I mean, just in looking at the Earth's atmosphere, all these like moon bows, and when you see a ring around the moon, or all these different effects are all particle scattering effects that aren't really spherical Mie scattering, because you have different shaped grains. So certainly eventually we'll have data that's good enough, and whether the near-term data is good enough, I don't know. But I think Mie scattering is probably okay for now, modulus the important point. I think the dirty grain certainly we can see, maybe even now. I think we had a question down here. Yeah. The importance of I kind of skipped over it, but the importance of the broad wavelength coverage really can't be overstated. And for the solar system, the lesson from the solar system clouds, I'm sure we'll hear more about that this week, is broad wavelength coverage helps you nail down particle sizes, cloud properties. So of course, as always, the answer is we just need more. Depending on what kind of object you're talking, like JWST will be really useful for that, right? You'll get like 1 to 10 microns, and I think that'll be very informative. But it sort of depends on like what would be the next step for. Sort of depends on the particular object you're thinking of, or the different class of objects. Right, so you have to separate, like I was giving you, like the Mies theory gives you the opacity for like one individual particle. And then when you have an agglomeration like a cloud, you have multiple, so your radius of transfer for how does the light get through the cloud or interact with the cloud definitely depends on multiple scattering. And so there's just all levels, different levels of complexity in how you treat that. We use something fairly simple. I think Pat will be talking like adding doubling codes are more sophisticated than what we, for example, use, but you need for the solar system. And so doing brown dwarfs right, especially as the data gets better and better, probably the treatment of multiple scattering needs to be better. Yeah, so you're getting different information all the way through. And I think like in the solar system, people sometimes will use a limited wavelength range, to study a given region of the atmosphere and what the opacity is doing or the abundances are doing there, and to kind of bootstrap your way through. And maybe that's the right approach we should be taking instead of trying to fit everything, from scratch all at once. There hasn't been enough. I mean, with all the my big complaint about all of the cloud models, ours included, is we don't double back enough, because everybody gets data and you want to fit it and write the paper, and so you get something, but you don't it never is the perfect match, and we don't spend enough time critically looking at where didn't it match, where did we fail, and what does that tell us to make it better. And that's my number one self-criticism is we don't spend enough time doing that. And I think as a field as a whole, we don't spend enough time doing that.
Okay, no more questions, so let's thank Mark again. So let's take a break now for coffee and maybe chat again around the poster, and we'll reconvene in 35 minutes for Mark's activity.
With the oscillation around the solutions, have you tried looking at